Hello, and welcome to this talk about container root file systems in production. I'm Claudia, this is Tiago, and we both work at Pivotal on an open source platform as a service called Foundry. I don't know, maybe some of you have heard of it, but don't worry, we'll go into that. So about a year ago, Foundry decided to create a team dedicated to providing the backing root file system for its containers. So in this talk, we're going to walk you through how we came to work with the file systems that Foundry containers use today. So here is a quick summary of what we're going to talk to you about. So first, we're going to go through a quick glossary of terms for those who have less familiarity with Linux file systems. Next, we will give a quick overview of Foundry for those who haven't heard too much about it, describing specifically the application runtime components. So we will describe the bits which actually run your app in the cloud and what CF needs to accomplish to do that successfully, CF being shorthand for Cloud Foundry. And then we are going to go through each file system which has been used in Cloud Foundry containers since the project began. For each one, we will explain why it was chosen, how we worked with it or around it, and why we decided to abandon it for another if that happened. At the end, we will briefly discuss what file systems we will be investigating in the future, and then finally, hopefully, we will have time for some questions. Okay, so before we start, I will go through the terms which we are going to be using in this talk. I won't go into too much detail, just a high-level illustration of things because we're nearly at the end of a long day and we don't want to spend all time learning about Linux, although I expect a lot of people here know lots about Linux. So for those of you who do know lots about Linux, so the experts, I apologize, but we're going to be saying the word file system a lot, so it's important that everyone knows what that means. So let's start simple. What is a file system? There are a couple of meanings associated with this term. The first is that it is the directory hierarchy used to organize files on a system. On Linux, the start of this tree is root /, in which there are subdirectories and then further subdirectories and so on. At least this is what it looks like to us. The Linux kernel has no notion of hierarchy, does not differentiate between directories or programs. It doesn't even identify files by name, but rather by inode. But we're not going to go into this. If you're interested to find out about inodes, just run ls-i on any directory, and you can see the number associated in the inode table. Okay, so the other meaning of file system is the type of file system, so how that storage of data is organized on disk within that file system hierarchy. So different types of file system have their own set of rules for controlling the allocation of disk space to files and for associating each file's metadata. In this talk, and in the case of containers, we're talking about both structure and type, and we care mostly about the second meaning, the type of file system. So we're going to be saying file system in terms of what it looks like, the structure, and the type of file system as in what is managing that structure, or the data within that structure. Because for large-scale systems, making the right file system choice for both the host and the containers running on it can have a very noticeable effect on performance. The wrong file system can really mess things up for you. So each file system brings its own set of tools and tricks for managing data, and these can react in sometimes unpredictable ways under load. And being prepared to face the risks and be ready to adapt is key. A multi-tenanted platform like CF has very specific requirements for what it needs to run many applications. The wrong file system type backing those application containers could be the difference between your app starting in 10 seconds and a minute. So next, what is a root file system? A root file system is the file system contained on the same disk in which the root directory is located. It is onto this file system that all other file systems are logically attached or mounted as needed at startup. I'm already using the word file system a lot. It's going to happen even more. So the root-of-s contents and directory structure, so the first meaning of file system, will vary with each operating system, but the root-of-s directory contains all the critical files necessary for booting the system and later keeping track of all running processes. The type of file system running and controlling this allocation of data for the root-of-s will also vary depending on how the system was provisioned. In this talk, we're going to be talking about root file systems a lot, as I've already said, And when we talk about the rootfs used to back Cloud Foundry, as I've already mentioned, we're going to be conflating the two. It bears repeating that twice. When it came to writing this talk, people were asking me, so what is a file system? And I know it instinctively because I say it all the time and I can differentiate, but actually explaining, annoying and difficult. So when we mention rootfs, we are talking about the structure and contents of the file system, which acts as the rootfs for applications, and we're also talking about the type of file system, or FS driver, which is managing data in that structure. CF needs to provide a type of file system to correctly assemble and manage the structure of the rootfs. And yes, that is a lot of jargon, so let's have a picture instead. A picture of a terminal, so not that exciting. Or it is, actually, because it's Linux. So here is a slide showing the top-level directory structure of a root file system of a Cloud Foundry machine on AWS. So all CF machines are deployed using what we call a stem cell. So a stem cell typically contains a bare minimum OS skeleton, in this case Ubuntu 14.04 on a 4.4 kernel, with some essential utilities and security config files pre-installed. All CF machines in a cluster on AWS can be provisioned using what is turned into an Amazon machine image, and end up with a host rootfs directory structure, which looks like this to us. So on the right, as you can see, I've run tree with a max depth of 1 from root. I'm obviously not going to go through each directory. I'm sure many of you recognize things like bin and user where binaries are stored, and proc where the process metadata is stored. So this is the root directory structure, so the first meaning of the word file system. Below, on the left, I've run df-mprint type. And on the first line of the output is the root mount point. This is where the rootfs directory is located. So that's where the structure on the right is located. We can see that the file system type of this VM's rootfs is ext4, so the fourth extended file system. We can also see that within root there are other file systems mounted. So we can see that there is another ext4 type of file system mounted in root, and also a tempfs type mounted on root. So this one looks very similar, but here is the directory structure inside the default root file system for containers on CF. This default option is built upon a version of Ubuntu. So the standard rootfs directory structure is pretty much the same as the one we saw previously. You can see that there is an app directory, which is symlinked to the containers, not the root's home directory. And this directory will hold the application code to be run inside the container. When the app runs, the system directories its users, so proc, bin, etc., are those within its own root file system, not the host root file system. But of course, the host root file system will keep track of various processes as well. And underneath the left, I have run df-mprint type again. The path names here don't actually mean anything, so ignore that. They're just to illustrate and show nested mounting. This time, if you look at the bottom line of that output, we can see that the running container's root file system is controlled by an overlay file system, which is mounted on a different file system, which is controlled by XFS, which is mounted on another file system, which is controlled by X4, and so on. So I hope that wasn't too confusing for the non-Linux people. Linux people, I'm sure you were fine. And now Tiago is going to explain how Cloud Foundry handles all this.
Cool. So just to add more words for glossary, what is Cloud Foundry, right? So it's important to introduce Cloud Foundry and what it is and what it does to get a better understanding of its requirements. Cloud Foundry is open source platform as a service. It was started being developed in 2009 at VMware. We first released around 2011. It's a big microservices project. It has dozens of repositories. It's mostly written in Go. Today, CF supports applications pushed as build packs or Docker images, and runs everything inside containers. Doesn't use Docker inside, but we're going to get to that. So what are build packs, right? The first versions of Cloud Foundry didn't have support for Docker images, for example, but you still could run your applications into containers. And that's where we use build packs for. Build packs are a set of scripts that provide framework and runtime support for applications. So they usually like language specific. This slide should have gone, sorry for that. Okay. So they're usually language specific because they'll compile your code, right? So to have better vision of that. So every time you push code to Cloud Foundry, what happens is like Cloud Foundry will create a container based on a root file system. We'll unpack inside the container the build pack and your application code. You will then execute the build pack, and that will create a droplet. A droplet is nothing else but like the compiled application. So it has everything that the application needs to run. So if it's a Ruby application, have all the gems installed. If it's a Go application, it's the compiled code. And it has everything that needs to run apart from the rootfs. That makes it easy for Cloud Foundry to move applications around from different VMs or scale them up, scale them down. So here's a demo of pushing an app to Cloud Foundry. So you can see there's no CF apps, there's no app pushed. I'm going to push this app, which is like a Ruby application, it's a very simple Sinatra application. The main command is CF push. You give it a name for application. You're going to upload all the files to Cloud Foundry. It's going to run through all the build packs available. It's going to automatically find the right build pack. In this case, it found like the the Ruby build pack, which means it's going to install the gems. Once the gems are installed, the build pack is created, and the application will be running. Any second now? Yes. So you can see there's a running application. Cloud Foundry automatically gave that application a routable URL. You can see there's one instance running. You can curl that endpoint. You get a response back, and it's also easy to scale. So if you want to scale to like 5 instances, for example, just CF scale command, and you have 5 applications running almost instantly. And if they are all routable from the same URL, so just get round robin around. So what were CF requirements at the time? So from the time that, since the beginning, it was a multi-tenant application. So that means you have organizations inside the same deployment. You can have different customers, all supplied by the same Cloud Foundry. It must be independent from the host FS. So when you run an application, you don't want the application to interfere with a host file system for obvious reasons. And it has application quotas from the start. So that means like memory quota, disk quota. We are going to talk about disk quotas here, but it's important to mention quotas because quotas is a big part of Cloud Foundry. It's how you avoid noise neighbors, for example. And at the time when Cloud Foundry was released, what was around, right? So the kernel was the 2.6 that we have on the Steam cells. You won't find mentions of containers as you do today. So even though Cloud Foundry was running what today we could call container, it wasn't like a broad term. And for example, there was no user namespace available at that kernel, which means you cannot use like isolation by the user, pretending to be a different user. And that was what we have at the time. And that brings us to our first solution.
First container implementation was called Warden. As Tiago just mentioned, containers weren't really the thing we know them as today. So at this point, they were more like isolated resource-controlled environments or something. Of course, that is what they are today. We just now have a cute name for them. Docker may not have hit its stride yet, and Docker is awesome, but it's important to remember that the containerization technology was already in play long before. We just didn't say containers yet. So Warden was the first simple API for CF. It was created in VMware and was written in Ruby and C to manage these isolated environments for CF as a daemon. Warden initially used the LXC, so the Linux Containers Project. But since Warden relied on only a small subset of LXC functionality, this tooling was then dropped with Warden implementing only what it needed. As Tiago says, the user namespace was not yet in the kernel, but others were. So for process isolation, Warden made use of the PID, mount, and network namespaces. Resources such as CPU, CPU set, and memory, but not disk, were managed by a C group created for each containers. So for those unfamiliar with these terms, Linux experts, go on Twitter or something. Namespaces and C groups are features of the Linux kernel, which when used together can effectively control the resources a process can see and access. So C groups partition tasks and their children into groups of specialized behavior. So i.e., they restrict what process trees can use. Namespaces wrap the process in an abstraction, which makes it appear to the process within that they have isolated access to a global resource, i.e., restrict what a process can see and therefore use. But that is containerization in general, and we all know about that. We're here for the file systems in this talk. So why AUFS? So AUFS is a file system type, second meaning, which originally stood for another union file system, but since version 2 has stood for Advanced Multi-Layered Unification File System, of course. So AUFS was developed in 2008 and is a complete rewrite of the Union FS. So along the same lines as Union FS, it implements a union mount to combine several directories in such a way that their contents appear to be under one single directory. AUFS aimed to improve performance and reliability of Union FS. And at the time, there were very few file systems mature enough to be used in the way that CF needed.
Sorry.
At this point, every container's root file system structure and base contents were identical. So mounting each one through AUFS was far more resource efficient than simply using copy to duplicate it everywhere. But AUFS was not available in the mainline kernel. It had to be patched in from an external module, which led to a lot of maintenance overhead for both the Warden team and the team responsible for rolling new stem cells. The kernel is pre-packed and modified to fit CF's needs at the time. Furthermore, AUFS had no native way to enforce user quotas, which was essential for multi-tenanted platforms. So the original team did what it could to make it work. So here is a very crude diagram, which gives a general idea of how Warden made CS requirements of scalability and user quotas work. The machines that containers were running on at this time were called DEAs, the Droplet Execution Agent, which ran the Warden daemon. These had a host root file system structure based on Ubuntu and using a file system type called X4. So that's the fourth extended file system. As Tiago has said, CF users could only deploy build pack apps. When you push your code, the language detected, the correct requirements are bundled along, and the application code is formed into a droplet. Then the droplet execution agent is deployed with a tarred Linux file system on its system, which each container can use as its base. So when an app is pushed, this root file system is untarred, and its contents serve as this base read-only layer. Warden then mounts each application instance onto this file system hierarchy using AUFS. The resulting thin read-write layer becomes the isolated root file system for the container. The droplet is then untarred, and the application code placed into the app directory we saw earlier. The app could run and make changes to its own read-write layer of the rootfs without affecting anyone else and without affecting the base. So a common rootfs mounted with a multi-layer file system, as I've said, is far more space efficient than simply using copy to duplicate the base layer dozens of times over and was therefore much more scale-friendly. As for CF's quota needs, application disk quotas were enforced by UID. Each application container was run as a different user on the host, with each user having its own resource limits enforced by the system quota control. For the purposes of this talk, this is where we leave Warden. The DEAs and Warden were obviously still in use as CF progressed. Still in use until really quite recently, I think. But obviously it had to be kept in play as we rolled out new components until they were fully production ready. But as we are interested for which type of file system that CF chose next, we're going to leave Warden here for now. So at this point, 2013, 2014, the ecosystem was changing rapidly, and the CF teams were always on the lookout for ways to improve upon their key container requirements. Around this time, the user namespace was introduced in newer kernel versions, and with that came a refreshed push for security and process isolation. At the same time, CF was growing and was looking for ways all its components could scale efficiently. Also, Docker came along, and our containers were the mot du jour. Exciting though Docker was, the team decided against using Docker's implementation of the Linux technologies because its stack was just a bit too unwieldy and big for us, and it was quite difficult to extract the few tools which were of use to CF's use case. Docker is also quite opinionated in that it tightly couples containerization and UX. It was the first to give us really quite lovely UX, but CF's one was different. So by continuing to leverage the specific containerization technologies from the kernel that CF needed, it could control the interface specific to our own use case.
Then the Garden Linux project was created around between 2014 and 2015. So what was Garden and Diego, right? So before that one, Warden, we have one big team that was dealing with the API, the scheduling, and the container runtime. And it was getting too crazy for one big team to handle. So the team was split, and 2 new teams were created. There was the Garden team that would be responsible for the container technology, and the Diego team that was the scheduler. So Garden is a replacement for Warden. So it's pretty much Warden written in Go, so they call it Garden. And Diego is the DEA written in Go, and they call it Diego. So Garden had all the old Ruby code replaced with Go, still using C underneath, and a lot of shell scripts, but was beginning of a rewrite. Diego, on the other hand, was completely rewritten and completely in Go. One of the reasons of creating the Garden project was the need to have this platform agnostic API. So Garden is actually an API, and you can have different implementations of the backend. So you have the Garden Linux, which is the Linux implementation of this backend. There's a Garden Windows, which is the Windows implementation and allows you to push apps to Windows platforms, for example. Cool. And initially, Garden was running the same EOFS implementation that Claudia just mentioned. But at some point, there was a feature request, and Cloud Foundry started supporting Docker images. The fact of supporting Docker images, just the fact to have support for Docker image changed things quite a bit. Because if you think about build packs, when you push an app on build pack, we control the rootfs. We have total control of all the rootfs that's going to be used. We literally own every file that will be going to be around the application. We also can control which user is going to run the application. But once you pull a Docker image, push a Docker image into the platform, and you execute it, you completely lose control of that, because the Docker image comes as a whole bunch of files, and you just have to trust it and execute it, right? And you also don't have control of the user, because the own Docker image spec allows it to run as a different user. And that brings up user namespace. So it's something you have to use to have security when running Docker images. But when you use Docker, when you have the Warden implementation before, what happened is like each container has its own user, and it was very easy to apply quotas, because you could say, oh, this user has X quotas, right? But once you start using user namespace, suddenly all the applications start running as the same user, and you completely lose control of this. You cannot use the same quota technique. So the old AOFS implementation was invalidated. So that made the team find a new solution, right? We have a need to find a new implementation for the file system, and we choose Beresford. So why BTRFS? So when the Garden starts supporting Docker image, it also brings with him the Docker graph code, graph driver code. So the choice of the file system would need to be something that was supported by the graph driver. All the other supported file systems were not quite good for us, because they or lacked maturity or features that we required. And Beresford was the only one that seemed to work. Also, Beresford had built-in quota support, which for us was a good thing. It's exactly what we need. So here's another demo. This one is shorter. It's just about how you push a Docker app into Cloud Foundry. You can see the command is pretty much the same. So I still have the old application running. I'm going to push a new application based on this Docker image. The only difference is the -o flag, right? And everything else is the same. You see there's no build pack stage on this one, because it's just going to download the image and run. But everything apart from that is the same. So it's the same user experience. You can scale the same way you scale a build pack app, and everything should just work. So you can see here there's one instance running. We can curl this endpoint, also get back response. You can scale to 5, and it's pretty much instantly done. Yep, you can see 5 instances running. 2 apps running, yeah. Here you can see also, well, it's gone, but you can see like the quota for each app. So even if Tiago and Garden were already tested in production using the old implementation, they're still quite new, right? So we're talking like months. And we had this new better fast file system going into play. we have, for the first time, we're changing our IS. So we're going to run on AWS for the first time. And there was a lot of changes happening. And yeah, they didn't go very well. So we had a huge performance drawback when we pushed this first time and started running in production. So because there were a lot of things happening at the same time, it was quite hard to point what was going on. Eventually, we have like a combined effort between all the teams, and we figure out that Beresford was the team to blame. At least we blame Beresford for the fail. And the theory we had at the time was like Beresford's garbage collection was just starving the machine. So it was consuming all the available IOPS from the machine, and in a way, it never recovered. So every time we had new IOPS, it just consumed garbage collecting and just trashed the machine. And because of that, we had to find a newish solution.
So yeah, back to this. After Beresford proved to be not quite production ready for CF, the team quickly switched back to a file system they knew and tolerated, not knew and loved, and they could get working again quickly. So I believe that within a couple of weeks, they had the new implementation, the new old implementation, ready to be rolled out. But the plan was still not to stay on AUFS, however. There was still no mainline support and still no native way to control application disk quotas. So the new implementation managed to do so like this. A formatted sparse file fixed to the requested app quota size was attached to a loop device and then mounted on top of the AUFS mounted file system. So a loop device is really a normal file, which when mounted acts like a block device, something with access to actual hardware or disk. An application could therefore not exceed the size enforced by the truncate, because the loop device believes that the size of its backing file is the total size of the disk it thinks it's writing to. So although this trick solved the quota problem, it had an impact on scalability. Loop devices are limited at a max of 255. So this imposed a hard limit on the number of containers CF could run per Tiago cell, which is the name of the component these containers were on. And therefore, you had to have a minimum number of Tiago cells to run them. So if you didn't plan ahead with enough capacity, pushing and scaling app instances could become a bit of a problem. So that was the state of CF and Tiago when, in 2015, RunC was released by the Open Container Initiative. And we were immediately certain that we wanted to be compatible with it. RunC provided a way to run containers without needing to start the Docker daemon and was far more flexible when it came to broad use cases. This was great news for CF because by getting Garden to work with RunC, we could have the best of both worlds. We get the best bits of Docker while complying with CF's user experience and having far less maintenance overhead for dealing with quite a large stack. We'd also be able to contribute back to the OCI community, which was nice because Cloud Foundry, all of Cloud Foundry's teams are open source, so we like getting involved and people getting involved with us. But we weren't in a position to get going right away with that, even though we wanted to start doing RunC things, because obviously CF was always growing, expanding, bandwidth problems, we couldn't get onto it right away. But then we eventually did.
Cool. So it was only around May 2016 that the Garden RunC started to be developed. So before jumping to Garden RunC, just a small introduction to OCI and Open Containers Initiative and RunC. I guess everyone kind of knows about it. So OCI created an open standard for container runtime, which is called Container Spec, and RunC was the implementation of that spec. So when RunC was released, like the Garden team was around between like the Garden Linux implementation and like releasing. They couldn't just do RunC yet, but as soon as they could, they start rewriting Garden again using RunC now. So the advantage of using RunC is that it's wrapping out the lower level parts of container creation. So we could just get rid of all the C code we had, all the syscalls, and all the like syscalls we had, and things that were just too much to maintain, and just use RunC instead and wrap that. And also, at the same time the Garden RunC was released, Cloud Foundry started pushing more security into the platform. So one of the objectives of the Garden team using Garden RunC was to provide a container runtime running completely in rootless mode. And that's still like And just like to emphasize how like the rootless part is important for security, because it reduces any exposure you have, like any surface area, quite a lot by not exposing the root user by the runtime. So, but even though Garden was great, well, I cannot say that, but like Garden is good, and there's a new implementation. It's still using the old AOFS, the previous AOFS implementation, and that was consuming quite a lot of time. So the same way before we had like this huge team that was doing too much, like 3 parts of the stack. You have now the Garden team dealing with container runtime and also file system management. It was consuming a lot of the team time, was like creating huge distractions, especially because AOFS was hard to maintain. Like it is a one-man project, and it's a huge project. It's every new kernel you have to patch, and you have to fix bugs. And because of that, around 2000, so because of that, between 2015 and 2016, other tools were getting created. So the OCI also created the image spec, which specifies a container image. And because that was like what we needed to split the team and start focusing into different areas. So the rootfs team, which is the Garden rootfs team, was created. It was a new project, and it should focus only on the file system bits of the container creation. And Garden then could be relieved and do just the security track that they were working on.
So this is where we come in. We are we're half of the rootfs team for Cloud Foundry. And as Tiago has said, it was decided that the next implementation of CF's container file system management should be done by its own team, not Garden, because they had enough things going on. From the start, rootfs was designed to be completely independent of Cloud Foundry. So the CLI tool could be used, or can be used to create a root file system from either a tarball containing a customized structure or a Docker image, both of which are then mounted and controlled by a file system type. We'll be showing you how rootfs works a little bit later. So in the sense of Cloud Foundry, when the Tiago cell needs a new container to be spun up, it would talk to Garden, and then Garden would talk to us, and then we would just throw out a root file system that Garden could then stick its container on. Because there was this push to get off AUFS, which, as Tiago has said, had not quite adequate support for our needs, the file system Groot was initially built around was BetterFS, which I'm sure as soon as you saw BetterFS on that slide, you were thinking, why? Because after the problems we had last time. Back then, as Tiago has mentioned, we weren't entirely certain what was causing those performance issues, but we had a pretty good working theory that it was caused by BetterFS's cleanup process. So before going back to BetterFS this time, we had to thoroughly test it and ensure it didn't happen again. So we managed to recreate the IOPS problem in an environment using a stem cell, so that's the skeleton that CF VMs are deployed on. And in this stem cell, it had the old 3.16 kernel that we had a year before. This time, once we recreated it, we then bumped the kernel to 4.4, deployed in our container VMs, and we saw that the high IOPS consumption wasn't happening this time. So after more extensive testing, we decided that the problem was fixed and that we were totally cool to go for it again. So the factors which had helped BetterFS progress and mature since the year before were things like big company investment and extensive testing in production environments. On top of that, it also had support from Canonical, which meant that CF could have more confidence in BetterFS as a production-ready file system driver. Aside from that stability, the features which had led us to choose BetterFS the first time around were still wanted and still true. Namely, BetterFS's built-in quota support and its ability to be, for the most part, rootless, which could one day be implemented in true unprivileged containers. The other useful feature was BetterFS's snapshotting mechanism, which works extremely well with image layering. So in this slide, you should see something which should be familiar to, I think, most people here. It's an illustration of an Ubuntu image. So when you pull a Docker image, it comes down in various tarred layers, which must be unpacked and then reassembled in a very specific order. Snapshotting allows you to build up each layer upon the previous one without needing to duplicate any of the files. So as many images have layers in common, this is very useful, because you don't want to end up storing the same potentially large layer several times over. So using Beresford, Groot unpacks the base layer and snapshots it. Then on that snapshot, it unpacks the next layer, snapshots that, and so on. Finally, the very last snapshot ends up being the read-write layer for your container. So here is another illustration showing the two different ways that your application can now be run on CF. On the left is the build pack root. Here there is only one layer, because the rootfs used for the build pack containers come from a single tarred file, which is then unpacked and snapshotted to produce the read-write layer, into which the droplet is then placed in the app directory. On the right is a Docker image-based app, in which each layer is untarred and snapshotted in order, with the last layer being the application layer. Note that here there is no droplet, because, of course, the app is built into the image as the read-only final layer. But predictably maybe, it didn't go as smoothly as we'd hoped. This time, however, we were actually ready. We had really good continuous integration infrastructure in place, and therefore caught the performance issues long before we went anywhere near production. And because of the dedicated team, we were able to swiftly diagnose the problem as related to Beresford and Groot, so us, and not anything else. It turned out that, sadly, by enabling Beresford quotas on a file system, there was a serious negative impact on performance. And CF components are often under load, scaling very fast, so our testing wasn't hard enough, apparently. Because CF is a multi-tenanted platform and sets resource quotas on every single app by default, there was no real option to turn off this functionality. It had to be done. We had to find a way. So we found another way.
Oh, so this is our current line of work. This is like we started this work in February 2017. As Claudia mentioned, the Beresford solution wasn't good enough. Like it was to a point, it wasn't production material for us. And we switched to overlay and an XFS driver. So why did we choose overlay and XFS? So we judged both projects to be mature enough for using. The way we use overlay is pretty similar to the way we use AFS also, which is combining layers. So overlay allows you to get different folders and put one on top of another and have a mount point with all those, the union of those folders, and also have like a read-write layer on top of that. But overlay alone doesn't support quotas, so that's why we need XFS. XFS adds supports for quotas to our solution. And also it's important to mention, like, even though Beresford wasn't good enough for production, it's still supported. Like, so this is just an addition of a new driver to GrootFS. Here's just a small illustration of how the current implementation works. As you can see in yellow is like an XFS folder. So each app instance, each container has its own application folder inside an overlay mount point, which gets a quota. And inside that mount point, we're going to create, inside that folder, we're going to create a mount point where the rootfs is going to be. So all the layers with that read-write layer on top will be mounted inside. There's a demo here that makes this a lot cleaner. So here is a demo of GrootFS in action. So GrootFS is a binary. It can be used independently from Cloud Foundry. You can just install with a go-get. Here's are the commands it has, like some options. You see it's in the temp store. That's what we call a store path. So a store path is where all the rootfs are going to be created. This one is already initialized, so it has a structure of folders. The most important here is like the volumes folder where all the layers of images will be, and the images folder where all the rootfs are going to be created. So if you use GrootFS and you give this store path, you say, I want the overlay XFS driver. I want to create a rootfs based in the Docker BusyBox image, and I'm going to call it my image. After some seconds, it needs to download all the layers. It prints out some JSON metadata. And if we list again the store path, you're going to see it changed. So now we have things in the volume. So that's because BusyBox has only one layer. You can see only one volume. And you can see in the image folder now there's a my image subfolder, which is that not container, but that rootfs path. If you look inside that folder, you can see now there's a diff folder and there's a rootfs folder. The rootfs folder is where is the overlay mount point. So you can see it has like a file system inside, a rootfs inside, and the diff folder is empty because that's the read-write layer. It creates another image we created here another image based in the same BusyBox, gave it a different name, so my image 2. You can see like the volume folders still have one layer because they're sharing the same layer. They're based from the same Docker image. At the same time, you have 2 folders now in the image folder, so one for each rootfs you created. If we, okay, go ahead, wait. Okay, so just, yeah. So if we list the contents of those 2 folders, you can see they are pretty much the same because they're based in the same image. But it's not showing here. OK, now it is. So if you create a file inside one of these images, folders, you're going to see it doesn't propagate to the other. That's because they're isolated, right? And you can see it appears in one of them. You can see it's in the diff folder because the diff folder where all the write operations actually happen. But it's not spread across the second one. And that's where we are right now. So we're still having a lot of tests, and we didn't go full production with this solution yet. But that's our current line of work.
Well, we're going to cut the next section anyway, because I've just been told that we are, right, where is it?
It's gone.
All right, OK, so it doesn't matter, we've got to cut now anyway. So I was going to tell you what we were going to do in the future for our next file systems. So those are X4 and ShiftFS. If you want to hear about them, you can come and find us afterwards. We'll be hanging around for like half an hour or an hour. I don't actually know, for some time. And Tiago, do you want to quickly wrap up?
Yeah, so I think that's our presentation. I think the things we want to bring here is that there wasn't a straight path from the beginning to here. And I don't think there will be one from now to the future. So it's important to always be ready to adapt. It's important to change. And one thing that worked a lot for us is like having a team focusing on a problem. So every time we split a team and we focus in the problem, we manage to advance much quicker. And that's how we work at Cloud Foundry. That's how we work on Pivotal. Thank you very much.